In this video, we're going to look at a common differentiation question, which is to show that a function is increasing, or in this case, strictly increasing for all values of x. So a few things to consider and to unpack there before we get going. First of all, what do we mean by increasing? Then how are we going to show that? What's our technique going to be? And how do we capture the all values of x part of the question rather than just one or two values of x? So first of all, what do we mean by increasing? Well, increasing values of a function just mean that the f of x values are increasing, they're getting bigger. So the values of a function, when we talk about the values, we mean the f of x values. So what we're trying to prove here is that for this function, the f of x values are always getting bigger. They never dip down, they never get smaller. But remember that f of x and y, when we're doing sort of algebraic geometry, working on an xy axis, f of x and y are the same thing. So we draw our horizontal axis as x, we draw our vertical as y, but the y is actually the f of x value. So what we're really talking about here is increasing means f of x values getting bigger, that means y values getting bigger. So thinking about that in terms of the graph, the graphical interpretation of this question basically means that the graph of the function has to always be going up. So in other words, strictly increasing is a fancy way of saying, hey, show that the graph of the function is always going up. We're not going to take a graphical approach, we're going to take an algebraic approach, but that's essentially what we're trying to prove. So let's just consider that for a moment to help us think about how we're going to do that, what our technique's going to be. If I draw some generic cubic function, so this is a cubic function, this is not our cubic function, I've just made up a cubic function here. Notice that here the y values are increasing here, but then they decrease here in this kind of middle point between the two stationary points, and then past that stationary point they start increasing again. So that graph there does not meet our criteria because it's not strictly increasing. Yeah, it's increasing here and it's increasing here, but it's decreasing here. It's going down at that point. So that's not what we're looking for. We're looking for a graph that goes something more like this, where it's increasing here. Actually, I've not drawn that very well. So let's say it's maybe still just increasing here and then increasing again here. So that's what we're looking for. Or to make it even more stark, that might actually be a stationary point, something like that. That would be the function y equals x cubed, which has just one stationary point at the origin. So that actually, that's quite a good mistake I've made there. Let's actually assume that that is horizontal. If that was horizontal, at that horizontal value, it's neither increasing or decreasing. It's actually stationary, flat. That's why we call them stationary points. That would also not meet our criteria here because we want strictly increasing. So if I had drawn this a little better, this is what I meant to draw, something more like this. This is increasing everywhere, always going up. So it's that kind of criteria there that's what we're looking for. This doesn't meet the criteria because it's increasing then decreasing. This doesn't meet the criteria because it's increasing and stationary, and this does meet our criteria because it's increasing everywhere, strictly increasing for all values of x. So how are we going to show this? Well, what are these little arrows really representing? They're really representing the gradient. So here we've got a positive gradient, this is negative, this is positive, here it's positive, then it goes to 0, then it continues on up again, so it's positive again. But this one, the one we're interested in, it's positive everywhere. So everywhere along this curve, the gradient is positive. But what is the gradient? The gradient is just the derivative, right? So gradient, m, slope, the way the angle, the slope, is just the derivative, f dash x, or f prime of x, if you call it f prime of x. So we're basically now saying that our problem is that we need to show that this is increasing by showing that its gradient or derivative is always positive. So we're trying to show that this is always greater than 0. So that's the graphical interpretation, which has kind of led us to this point here. So that's what we're trying to show. So we can really interpret this question as saying, show that for all values of x, the gradient, m, or the derivative, which is what we're going to use, is strictly greater than 0. So how are we going to do that? That is now what this is boiled down to. Well, let's start by taking our derivative. So we've got our function, we can take our derivative. So f dash of x, just using the normal power rule for this, so just differentiating as you normally would to get 3x squared for the first term. So just multiplying by the power and reducing the power by 1. So 24x for the second term plus 50. So we've now transferred the problem from this wordy interpretation to show the derivative is positive. We've now taken our derivative. We now need to show that that is always greater than 0. Okay, that's what we're trying to show. So I can't really write that in there yet because I've not gotten to the point of actually showing it. That's just what we need to show. So we've got our derivative. How can we show that that's always positive for all values of x? So you could start subbing values of x in here, but it doesn't matter how many values you put in. You could put in some negative values, some zero, well, the zero value, you could put in some positive values, but it doesn't matter how many of those you put in. You could never be fully satisfied that that is covering all cases for x. It might be that the next one, the one that you missed, is the one where it goes back to being negative. So how can we show in a more sophisticated way that this is always positive? Well, one way you can do this is, and you'll see this in a lot of question types, if you've got a trinomial, so a quadratic expression in trinomial format, and you want to show that it's greater than 0, then we're going to write it in completed square form. So completed square form, if you're not familiar with that, means that you take your trinomial and you write it in the form x plus or minus some a value, which will be a number, in a bracket squared plus or minus some b value. And you'll see in a moment why that's going to be useful. So if you're not sure about this technique, completing the square, maybe try and look that up in another video. I'm going to go through it fairly quickly here. The way that it works is you start by pulling out a common factor just from the numbers from the first two terms. So pulling out the 3, leaving, don't worry about the x. So x is a common factor here as well, but don't worry about that. So just pulling out the common factor, so you get 3 square bracket x squared plus 8 x, and then we're going to close the square bracket. We're only using a square bracket because we're going to put a round bracket inside the square bracket in a moment just to keep it cleaner. So this then becomes 3, and this is a completing the square part. So we do x plus 4 all squared minus 16, leave the plus 50 on the end. Now, it would take me a while to explain why I go from here to here, but basically that and that are the same thing. So if you're watching this video and you're doing differentiation, your algebra is already going to be pretty good, I assume. Just check these two. So multiply this bracket, see what you get, and make sure that these two things are indeed equal. This is just a rewriting of this in a different form to match this completed square form, okay? So the technique to go from there to there, I'm not going to explain that here. I'm going to assume you know how to do that. If not, just satisfy yourself that those are the same thing. So what we're going to do now is multiply out the square bracket. So multiply the 3 to the round bracket and you just get 3. You can't multiply that into the round bracket, so we're just going to park it in front like that. 3 times minus 16 is minus 48, and we've still got the plus 50 on the end. Just taking that one step further, just to combine these end two numbers. So 3 bracket x plus 4 all squared, minus 48 plus 50 is plus 2. Now remember what the goal was here. The goal was for us to show that the derivative is always greater than 0. This is our derivative, but these are all the same thing. So this is just this in a different form. So this final line here is also the derivative, f prime of x. Is that always greater than 0? That's what we're trying to show. Well, how is that useful being in this form compared to that form? Well, it's useful because anything inside a bracket squared, or indeed any number squared, is always going to be positive. So this term here, bracket squared, has to be positive. It doesn't matter if you put a negative value in there for x. Even if you square a negative value, you still get a positive return on that. So that's always positive. Taking a number which is positive and multiplying it by 3, well, that's just making it more positive, right? So that term is definitely like positive. Adding 2 to that is making it even more positive. So you're starting off with a positive number and making it more positive and then more positive again. So it doesn't matter what x you put in there, that is always going to be greater than 0. Okay, so by changing the form of our derivative into this completed square form, we can conveniently see that that has to, just by a kind of logical argument, has to always be greater than 0. That shows that our derivative is always greater than 0. That means that we've got some kind of graph that goes like this, because a derivative is just a gradient. If it's always greater than 0, it's always sloping up. That proves then that this function is strictly increasing for all values of x. Notice even that if you put minus 4 in here, so minus 4 would give you a 0, and 3 times 0 is still 0, but you'd still be adding 2, so that would still come out to be positive. So there's no way to even make this 0. It's not greater than or equal to 0, it's strictly greater than 0 for all x. So that means that this scenario could never even happen, it has to be this scenario. So that basically proves that this function is strictly increasing for all values of x. If you're ever asked to show that a function is increasing or decreasing, either at a single point or on a range of values, or indeed for all values, it's all going to come down to the fact that gradient and derivative are the same thing, and increasing just really means that the graph is going up, which means that the gradient or the derivative has to be greater than 0. So a tricky little problem, but one that kind of highlights the power of derivatives and the fact that a derivative links back to a gradient, which links back really to the behavior of the function. Is the function going up? Is it going down? Is it stationary? What is it doing? We can explore that by using the derivative. And this one just happened to use a little bit of, I dare not say basic algebra, but fairly basic algebra. So I hope that that problem and that solution makes sense. If you've got any questions or comments, just leave them in the box below.